Okay, so today we're looking at optimization problems. So our learning intention is to gain knowledge in using calculus to determine solutions to optimization problems. To be successful, we really need to understand what the question's asking us to do. We really need to be able to draw a diagram that represents that and use the necessary formulas or constraints to determine the function. We have to apply our differentiation skills, find stationary points and determine their nature, and consider the reliability of your answer. Okay, so let's try one example here. Optimization problem is trying to find the absolute maximum minimum of the problem. So we've got the cost per hour of a bike ride is given by this current formula, where x is the distance travelled in kilometres. We want to find the distance that gives the minimum cost. Okay, so what I'm going to do is I'm going to differentiate it first. I'm then going to set the derivative to be 0 so I can find the stationary point. Alright. If I differentiate that, that gives me x equals 2, which is 0, so it looks like this is, it doesn't tell me much here, so I'm not going to, that doesn't really help me. But I know it's a parabola, and I have a stationary point at when x equals 7.5. It's a positive parabola, so it looks like that. So the minimum cost would be at that stationary point. So therefore, the minimum cost will be to travel 7.5 kilometers. Okay, this second derivative just told us that the function is increasing. Okay, example 2. We have the difference of two numbers is 5, so let's two numbers be x and y, such that x minus y equals 5. Find these numbers if their product is going to be 1, so the product is going to be less than 0. Okay. From equation 1, I get y equals to x minus 5, and subbing that into 2, we get x times x minus 5 is less than 0. So x squared minus 5x. So the equation. Alright, if I differentiate that, I get 2x minus 5. If I let that equal to 0, I get the first number of 5 on 2, or 2.5. Okay, sub x is 2.5 into equation 1, you get 2.5 minus y equals 5, so y equals negative 2.5. Therefore, the two numbers are negative 2.5 and 2.5. Okay, another example. We have a rectangle that's cut from a circular disc of a radius of 6 centimeters. we want to show that the formula for the area of the rectangle is such, and we want to find the area of the largest rectangle can be produced. So here's my circle. It has a radius of 6, which means it has a diameter of 12. But what I'll do is from this diameter, okay, I'm going to draw my rectangle. Okay. Looking at this square, I can use Pythagoras. So looking at this triangle, I can use Pythagoras that x squared plus y squared equals 12 squared. Yeah, so x squared plus y squared equals 144. Or y would be the square root of 144 minus x squared. Okay. But the area of the rectangle will be x times y. So subbing our y values, the area would be x multiplied by 144 minus x squared, which gives us the formula that we wanted. Okay. Now we want to find the largest area. So the first thing we need to do is to differentiate that. So this is using the product rule. It works out to be that. Okay, we want to find the stationary points. So there's no point doing it at the bottom, so we want the top to be set to 0. So I get x equals the square root of 72. Alright, using this back into this situation, so subbing x equals root into your original equation, so we're going to find the largest area. So the largest area is at 72 centimeters squared. Okay. One more example. We have a rectangular field. It's to be fenced with 500 meters of material, and a building is on one side of the field. So that building won't be required to be fenced. So I'm going to draw a diagram first. So this is the building, and I won't need to fence that. So in this situation, the perimeter would be 2x plus y. Now the perimeter is going to be using 500 meters of fencing. Okay, I want to determine the maximum area. So area is going to be still x times y, but subbing what we have for y, we get area is equal to x lots of 500 minus 2x, which is 500x minus 2x squared. If I differentiate that, I get 500 minus 4x. If I let that equal to 0, I get x being 125. Okay. Subbing x, that's being 125, into my original formula, we get 500 lots, 2 lots of 125 plus y, we get y being 250. So that will be, so the dimension of the field that will enclose the largest area is the width of 125 and length of 250. And that's how we found an optimization problem. Okay, good luck.